Okay, we are going to look at rational functions next. And I got to tell you, they look they originally look a whole lot like reciprocal, but they are rational functions. And whenever I abbreviate them, I always abbreviate it as rat fun, which I think is funny because rats are not fun, but see, fun, rat, get it? Anyway, okay, rational functions. Here we go. Rational functions do look a lot like a reciprocal, and I would call them a close cousin, but they get crazy. So here's the definition that we're going to talk about of a rational function. Oh, I think I gave you a sheet for this. Let me find it. Hold, please. Hold, please. Hold, please. Hold, please. Hold, please. Ah, yes, here it is. Ta-da! Oh, no, just kidding. Reverse. Okay, got it. Here we go. Rational functions. So, let's get a definition of this thing. A rational function is a function that can be written as, wait for it, f of x equals p of x divided by q of x, when p of x and q of x are polynomials, and guess what about q? And q of x, what can q of x not learn? What do we learn in reciprocals? It cannot equal 0. So you can't have a 0. We know that. It's undefined. So here are some examples of what this can look like. So it can be something as simple as like 20 over x. All right? This looks very reciprocal-ish, except what is not on top? A reciprocal has a 1 on top because we were taking a function and taking its reciprocal. Here, we're not taking a reciprocal. A rational function is a rational function. It didn't stem from somewhere, if you will. It could also look like this. It could be like 2x plus 30 over x. Or it could be like super crazy. It could be like 4x squared plus 3x over x plus 5. So these are all rational functions. They all have a function in the numerator and a function in the denominator. So they really can come in any form. And again, they are not like stemming from the reciprocal, right? They just kind of are. So q of x, let's take note, q of x cannot be 0. Therefore, we must find the non-permissible value. And do you want to take a shot in the dark at what it's going to do? It's going to cause a vertical asymptote. You are right. Okay, so let's look at what this looks like. Let's just try one, shall we? So let's come on down here. Let's do f of x equals 10 over x. So this is a rational function. There is no parent, if you will. Like, we're not working backwards or doing any of that. What value is going to be my non-permissible value here? What value is not allowed? 0, right? So x cannot be 0. That would give me something undefined. So let's make ourselves a little quick table of values just for funsies. So here's my x, here's my y. I'm going to go -50, and then I'm going to go -10, -5, -1, 0, 1, 5, 10, and 50. And let's see what happens. How does this look different than my, like a reciprocal function? So if I do this, I'm going to substitute these x's in here. So I'm going to have 10 over negative 50, and that's going to give me negative 1/5. And 10 over negative 10 is going to give me negative 1. 10 over negative 5, negative 2. 10 over negative 1, negative 10. 10 over 0, undefined. 10 over 1, 10. 10 over 5, 2. 10 over 10, 1. 10 over 50, 1/5. Okay, let's go graph these and see what happens. So I'm going to go, who gave me a graph that goes to 15? I'm going to call this, okay, we're going to put 50 way over here, and 50 is only going to be up at 1, oops, it's going to be down at negative 1/5. At negative 10, I'm down to negative 1, negative 5, negative 2. Nothing at undefined. I'm going to go over 1 and up 10, and then I'm going to go over to 5 and up to 2, and then I'm going to go over to 10 and up to 1, and I'm going to go over 50. It's way over here. And look what happened here. I forgot that one. Negative 10. So guess what's happening? The same similar situation is happening. It's doing this, and we are getting 2 branches again. So we've seen this before. And where's our horizontal asymptote? Well, it is happening right here at 0 because that's where my non-permissible was. That's great. And can you see that I've also got a horizontal asymptote happening here? This is happening at 0 because as x gets large, what is y approaching? So, like, look right here. If I had 10 over 2,000, what is x approaching? That's about 0. And if I had 10 over 5 million, what is x approaching? 0. So this is going to continue to be my horizontal asymptote if you can keep that thought in mind. So unlike reciprocal functions, we don't have an x-intercept here because we don't have a second function, right? Like all we have is a rational function. Let's discuss, let's kind of summarize here. So our vertical asymptote is at 0. Our horizontal asymptote also at 0. I can really do domain and range now because it's pretty straightforward. So my domain is going to be x is an element of all real numbers, but x cannot be what? X cannot be 0. Range is the same. Range is the element of all real numbers, but y cannot be 0. And then we're going to go back to talking about end behavior. We touched on this earlier in the year. So end behavior, we're going to write like this. As x approaches 0. So as x approaches 0, so that means like as I'm coming in here. Okay, what is y doing? Y becomes very large, right? Doesn't that make sense? Like, look what's happening. As I get closer and closer to 0, as my x's are getting closer to 0, where's my y going? It's shooting straight up. And as my x gets closer to 0 here, my y is still getting large, although it's getting large in the other direction. The value of it is very large, the distance. Okay, let's try another one. Okay, let's look at, I think you've got another one of these on the back side of your sheet. Okay, so you've got this. All right, let's do something crazy. Okay, not crazy, but y equals 20 over x plus 1. All right, so this is a rational function. First and foremost, what is my non-permissible value? What would give me 0. So set the denominator equal to 0 and solve. So my non-permissible value here is x equals -1. Perfect. Now, where do I expect to have a vertical asymptote? I expect it to be at the exact same place as my non-permissible value. So let's go make ourselves a nice little table of values. All right, let's go. I'm going to pick numbers that are going to work for me here. So I'm going to say -11, -6, -2, -1, 0, 1, 5, and 9. Okay, if I plug these in, -1 plus, or -11 plus 1 is -10. 20 divided by -10 is -2. -6 plus 1 is -5, so 20 divided by -5 is -4. -2 plus 1 is -1, so 20 divided by -1 is -20. -1 plus 1 is 0. 20 divided by 0 is undefined. Okay, 20 divided by 0 plus 1 is 1, so 20. 1 plus 1 is 2, so 20 divided by that is 10. 5 plus 1 is 6. Who picked that number? Let's make that a 4. 4 plus 1 is 5, so that gives us a 4. And 9 plus 1 is 10, and that gives me a 2. All right, let's go graph this and see what we get. So we're going to say -11 and -2 and -6 and -1, 2, 3, 4, -2 and -20. Oh dear, like down here. And then -1 is undefined. So break out your highlighter and go give yourself a vertical asymptote that runs up and down here. Okay, 0 is 20. So I'm going to come way up here on 0. 1 is 10. 4 is 4. Is that right? 9 is 2. Okay, so what's happening here? We've got 2 branches again. All right, we have 2 branches, but can you see that this has a much larger distance from the center, if you will, than we used to? That's because this 20 is functioning like a stretch. So that 20 on top is acting like a stretch, so it's kind of pulling our graph away from the center. Now, where do you see us having a horizontal asymptote here? I see it right here at 0. Now, it's going to move, but it eventually this week, but for right now, it is right there. So we have a vertical asymptote at -1. We have a horizontal asymptote at 0. Do we have any invariant points? No, we don't, because there's nothing to cross paths with. There's no other function. So don't go looking for invariant points. They're not there. What else do we have? We have end behavior. And what's our end behavior doing here? As x, and a lot of times we talk about x as the absolute value, so we don't have to talk about the direction of x. So we can say as x approaches 0, what's happening to y? Y gets large. What else is happening that you think we should talk about? The domain and range. We have a domain that is x is all real and x is not -1. And our range is y is all real numbers and y cannot be 0. Okay, so that's all we're going to cover for today. So as a recap, rational functions can have whatever they want in the numerator and in the denominator. So this is different than reciprocals because reciprocals had a 1 in the numerator. We still have a non-permissible value, and that leads to a vertical asymptote. We still have a horizontal asymptote. We still have domain. We still have range. And we're going to start now talking more about end behavior. Okay, I hope that made sense. Great job.